Welcome to the second part of our Dart journey. If you've mastered the basics of variables, functions, and control flow, you're ready to take your Dart skills to the next level. Before we dive into intermediate concepts, let's quickly review what you should already be comfortable with. You should understand basic Dart syntax, know how to work with variables and data types, create functions, use control flow statements, and work with collections like lists and maps. Perfect. Now let's explore what you'll master in this intermediate series. We'll cover 4 major areas that will transform you from a beginner to an intermediate Dart developer. First, you'll master object-oriented programming, the foundation of modern software development. You'll learn about classes, inheritance, polymorphism, and how to structure your code like a professional developer. Next, we'll explore asynchronous programming using futures and async await. This is crucial for building responsive applications that can handle multiple tasks without blocking the user interface. Then you'll learn file handling and package management. You'll discover how to read and write files, manage dependencies with pubspec.yaml, and leverage the rich ecosystem of Dart packages. Finally, we'll cover testing and code quality. You'll learn to write unit tests, ensure your code is robust, and follow best practices that professional developers use every day. But here's the exciting part. You won't just learn theory. We'll put everything together by building a real command-line note-taking application that demonstrates all these concepts in action. This project will include object-oriented design, file operations, error handling, unit testing, and proper package management. By the end, you'll have built a fully functional application that showcases your intermediate Dart skills. Are you ready to level up your Dart skills? This journey will transform how you think about programming and give you the tools to build professional quality applications. Let's start building some cool stuff together. Dart is fundamentally an object-oriented programming language. This means everything in Dart revolves around objects, entities that combine data and the methods that operate on that data. Object-oriented programming is built on 4 fundamental principles, often called the 4 pillars of OOP. These principles guide how we structure and organize our code. To understand these concepts better, let's look at a practical example. Here we see how a dog class demonstrates object-oriented principles. It has attributes like height and weight, and methods like run, play, and eat. Encapsulation is about bundling data and methods together within a class, while controlling access to that data. It's like putting related things in a container and deciding what others can see or modify. Inheritance allows one class to inherit properties and methods from another class. This promotes code reuse. A child class gets all the features of its parent class and can add its own unique features. Polymorphism means many forms. It allows objects of different classes to respond to the same method call in their own unique way. The same method name can behave differently depending on which object calls it. Abstraction is about hiding complex implementation details and showing only the essential features. It's like using a car. You don't need to understand the engine mechanics to drive it. You just use the steering wheel and pedals. These 4 principles work together to make Dart code more maintainable, scalable, and easier to understand. They form the foundation that makes object-oriented programming so powerful for building complex applications. Encapsulation is one of the fundamental principles of object-oriented programming. It's about bundling data and the methods that operate on that data together within a class. Think of encapsulation like a protective container. Inside this container, we bundle together related data and the methods that work with that data. Inside our class container, we have data variables that store information and methods that can manipulate or access this data. Now let's see how this works in Dart code. We'll create a simple bank account class that demonstrates encapsulation principles. Here's a bank account class. Notice the underscore before the balance variable. This makes it private in Dart, which means it cannot be accessed directly from outside the class. The underscore prefix makes these variables private. This is Dart's way of enforcing encapsulation. External code cannot directly access or modify the account number or balance. Encapsulation also means providing a controlled public interface. The class exposes only the methods that external code should use, while keeping the internal implementation hidden. This approach provides several key benefits. data protection, controlled access, and the ability to change internal implementation without affecting external code that uses the class. To demonstrate encapsulation in action, here's what happens when we try to access private data directly. Dart will prevent this access, protecting the object's internal state. Encapsulation is essential for building robust, maintainable code. By bundling data and methods together and controlling access through private and public members, we create safer and more predictable programs. Inheritance is one of the fundamental pillars of object-oriented programming. It allows us to create new classes based on existing ones, promoting code reuse and establishing clear hierarchical relationships. When a class inherits from another class, the inheriting class is called a subclass or child class, while the class being inherited from is called the superclass or parent class. In Dart, we use the extends keyword to create inheritance relationships. Let me show you a practical example with code. Here's a simple example. We start with a vehicle class that has common properties like brand and year and a method called start. Now, let's create a car class that inherits from vehicle using the extends keyword. Notice how car automatically gets all the properties and methods from vehicle. The super keyword is crucial in inheritance. It allows the child class constructor to call the parent class constructor, ensuring proper initialization of inherited properties. Let's look at a more comprehensive example using a banking system. This diagram shows how different account types can inherit from a base bank account class. In this hierarchy, bank account is the superclass containing common properties like owner and balance, plus methods like deposit and withdrawal. Checking account and savings account inherit these features while adding their own specific functionality. Here's another way to visualize inheritance. This shows how an animal class can be extended by a bird class, which then creates specific bird objects with both inherited and new methods. Notice how the bird class inherits the sound method from animal, but also adds its own chirp method. When we create a bird object, it has access to both methods. This is the power of inheritance. Inheritance creates hierarchical relationships. Here we see a shape superclass with multiple subclasses like square, circle, and triangle. Each subclass inherits common shape properties while implementing their own specific behaviors. Let's see inheritance in action with a practical code example. Here's how we can create and use objects from our vehicle hierarchy. The key benefits of inheritance are clear. Code reusability means we don't repeat common functionality. Hierarchical organization makes our code structure logical and maintainable. And extensibility allows us to easily add new features to existing classes. Inheritance is a powerful tool that makes your Dart code more efficient, organized, and maintainable. By understanding how to use extends and super, you can create robust class hierarchies that promote code reuse and clear relationships between your objects. Polymorphism is a fundamental concept in object-oriented programming that allows objects of different classes to respond to the same method call in their own unique way. The word polymorphism comes from Greek, meaning many forms. In programming, it means that the same method can behave differently depending on which object calls it. Method overriding is one way to achieve polymorphism. Here we have an animal parent class with a makeSound method. The dog and cat classes extend animal and override the makeSound method with their own implementations. Each class responds to the same method call differently. The override annotation tells Dart that we're intentionally replacing the parent method with a new implementation. This class diagram illustrates polymorphism perfectly. We have 3 different classes that all extend a school class, and each implements the number of students method in their own way. In Dart, any class can act as an interface. Here, the drawable class defines a contract that other classes must follow when they implement it. The power of polymorphism shows when we use these objects. We can treat different objects the same way, calling the same method on each, but getting different behavior. This UML diagram shows another example of polymorphism through inheritance. The subclass inherits from superclass but overrides both the attribute and operation with its own implementation. Polymorphism provides several key benefits. It makes code more flexible and reusable, easier to maintain and extend, and creates a cleaner, more organized code structure. Polymorphism in Dart is achieved through method overriding and interface implementation. It allows the same method call to produce different behaviors, making your code more flexible and maintainable. Remember, any class in Dart can act as an interface, giving you powerful design options. Abstraction is one of the fundamental principles of object-oriented programming. But what exactly does it mean to hide complexity? Let's explore this concept with a real-world example. When you see a car emitting smoke, you might wonder how this is happening. But as a driver, you don't need to understand the internal combustion engine, fuel injection systems, or exhaust mechanisms. You simply know that pressing the gas pedal makes the car move. This is abstraction in action. Abstraction is the process of hiding complex implementation details while showing only the essential features and functionality that users need to interact with. In computer science, abstraction works through different levels. Let's examine how this layered approach helps manage complexity in software systems. The view level represents what users see and interact with. The logical level contains the business logic and rules. The physical level handles the actual data storage and hardware interactions. Each level abstracts away the complexity of the levels below it. In Dart programming, abstraction allows us to create classes that expose only the necessary methods and properties. Let's see how this works with a simple example. Notice how the internal details like engine type and fuel level are private, marked with underscores. Users of this class only see the public methods like start engine and drive. They don't need to know how the engine works internally. Abstraction provides several key benefits in software development. It reduces complexity by hiding unnecessary details, improves code maintainability, and allows for better organization of large systems. Think of abstraction as creating a simplified interface for complex systems. Just like you don't need to understand how a smartphone's processor works to send a text message, abstraction in programming lets you use objects without knowing their internal implementation. Classes, objects, and constructors are the fundamental building blocks that bring object-oriented programming to life in Dart. Understanding these concepts is essential for creating well-structured, maintainable code. A class serves as a blueprint or template for creating objects. Just like an architectural blueprint defines the structure of a building, a class defines the properties and methods that objects will have. Objects are instances created from a class blueprint. Each object has its own set of property values, but shares the same structure and methods defined by the class. Constructors are special methods that initialize objects when they are created. They set up the initial state of an object by assigning values to its properties. Dart supports several types of constructors. The default constructor is automatically provided if no constructor is defined. It initializes objects with default values. Parameterized constructors accept arguments to initialize object properties with specific values. This allows you to create objects with custom initial states. Named constructors provide multiple ways to create objects from the same class. They have descriptive names that indicate their specific purpose. Factory constructors provide more control over object creation. They can return existing instances from a cache or create objects conditionally. Constant constructors create compile time constants. They ensure that objects with the same values are identical instances, improving memory efficiency. Understanding the relationship between classes, objects, and constructors is fundamental to object-oriented programming. Classes define the structure, constructors initialize the objects, and objects are the working instances in your program. Optional parameters in constructors provide tremendous flexibility when creating objects. Instead of requiring all parameters every time, we can make some parameters optional with default values. Let's start with positional optional parameters. These are enclosed in square brackets and can have default values. Here's a person class with optional age and city parameters. Now let's see how flexible this constructor is. We can create person objects with just a name, with name and age, or with all three parameters. Each call is valid and uses appropriate defaults. Named optional parameters offer even more flexibility. They're enclosed in curly braces and can be called in any order. This makes the code more readable and self-documenting. Named parameters shine when creating objects. You can specify only the parameters you need in any order. making the code much more readable and maintainable. You can also make named parameters required using the required keyword. This ensures certain parameters must be provided while keeping others optional. Optional parameters eliminate the need for multiple constructor overloads. Instead of creating separate constructors for different parameter combinations, one flexible constructor handles all cases, making your code cleaner and more maintainable. Optional parameters in constructors make your classes more versatile and user-friendly. They provide flexibility in object creation while maintaining clean, readable code. This is a powerful feature that every Dart developer should master. Mixins are a powerful feature in Dart that allow you to reuse code across multiple class hierarchies. Unlike inheritance, which creates a parent-child relationship, mixins let you mix functionality into classes from different hierarchies. A mixin is a special type of class that provides functionality that can be mixed into other classes. Think of it as a toolbox of methods and properties that multiple classes can use. Here's how we define a mixin in Dart. We use the mixin keyword followed by the mixin name. This flyable mixin provides flying functionality that can be shared across different classes. To use a mixin, we use the with keyword after the class name. Here, both bird and airplane classes get the flying functionality from the flyable mixin, even though they're completely different types of objects. The on keyword lets you constrain which classes can use a mixin. Here, the swimmer mixin can only be used by classes that extend animal. This ensures the mixin can safely call methods from the animal class. This diagram shows how mixins fit into class hierarchies. Unlike traditional inheritance trees, mixins allow horizontal code sharing across different class families, promoting better code reuse and modularity. Mixins provide several key benefits. They enable code reuse across different class hierarchies, help avoid the diamond problem of multiple inheritance, allow you to compose functionality from multiple sources, and maintain a clean, modular code structure. Here's a practical example showing how a class can use multiple mixins. The duck class combines walkable and swimmable mixins, giving it both walking and swimming abilities, along with its own quack method. This demonstrates the power and flexibility of mixins in Dart. Abstract classes serve as blueprints for other classes. They define common behaviors and properties that subclasses can inherit and implement, but cannot be instantiated directly. Think of an abstract class as a blueprint. Just like architectural blueprints define the structure for buildings, abstract classes define the structure for other classes. Here's a practical example. We have an abstract person class that serves as a blueprint for customer and employee classes. Notice that person is marked as abstract. It defines common properties like name, surname, and type that both customer and employee inherit. Now let's see how this looks in Dart code. Here's how we define an abstract class. The key feature is the abstract method calculateArea. It has no implementation, just a declaration. Subclasses must provide their own implementation. Here's how a subclass implements the abstract method. Each subclass provides its own specific implementation. Remember, you cannot create instances of abstract classes directly. You can only instantiate the concrete subclasses. Here's a real IDE example showing abstract classes in action. Notice how each subclass provides its own implementation of the abstract method. Abstract classes provide several key benefits. They enforce a common interface, promote code reusability, and ensure that subclasses implement required methods. Abstract classes are essential blueprints in object-oriented programming, providing structure while allowing flexibility in implementation. In Dart, interfaces define contracts that classes must follow. Unlike many other programming languages, Dart doesn't have an explicit interface keyword. Instead, any class can serve as an interface. Let's see how this works in practice. Any class in Dart can act as an interface. Here's a simple example where we define a class that will serve as our interface. Now, to implement this interface, we use the implements keyword. When a class implements an interface, it must provide concrete implementations for all the methods defined in that interface. It's important to understand the difference between implements and extends. When you extend a class, you inherit its implementation. When you implement an interface, you only inherit the contract. You must provide your own implementation. There's an important restriction to remember. Libraries outside of the interface's defining library can implement the interface but cannot extend it. This ensures proper encapsulation and prevents unintended inheritance. Let's look at a practical example that demonstrates these concepts in action. Here we can see how interfaces work in a real Dart program. Interfaces are powerful tools for creating flexible, maintainable code. They allow you to define contracts that multiple classes can implement in their own way, promoting code reusability and polymorphism while maintaining clear boundaries between different parts of your application. Error handling is crucial for writing robust Dart applications. When things go wrong in your code, Dart uses exceptions to signal these errors, and you need proper mechanisms to handle them gracefully. The primary mechanism for handling exceptions in Dart is the try-catch block. The try block contains code that might throw an exception, while the catch block handles any exceptions that occur. Now let's add the finally block. The finally block contains code that always executes, regardless of whether an exception was thrown or caught. This makes it perfect for cleanup operations. To better understand the execution flow, let's examine this flowchart that shows exactly how try-catch finally blocks work together. The program first executes the try block, then checks for exceptions and matching catch blocks. The flowchart shows the decision points clearly. After executing the try block, the system checks if there's a matching catch block for any exception. Then, regardless of what happened, the finally block always executes if it exists. Let's see this in action with a practical example. Here's a function that reads a file and will handle potential errors like file not found or permission denied, while ensuring we always close any resources in the finally block. This example demonstrates robust error handling. The try block attempts the risky file operation, the catch block handles different types of exceptions appropriately, and the finally block ensures cleanup always happens, making your code more reliable and maintainable. Asynchronous programming is a fundamental concept in modern software development that allows programs to perform multiple tasks concurrently without blocking the main execution thread. To understand asynchronous programming, we first need to see the difference between synchronous and asynchronous operations. In synchronous programming, tasks execute one after another, with each task waiting for the previous one to complete. In Dart, asynchronous programming is primarily handled through future and stream objects. A future represents the result of a single asynchronous operation that may not be immediately available. A future acts as a placeholder that will eventually contain the result of an asynchronous operation. While the operation is running, your program can continue executing other tasks instead of waiting. Stream objects represent a sequence of asynchronous events. Unlike future, which provides a single result, stream can emit multiple values over time, making it perfect for handling continuous data flows. The key advantage of asynchronous programming is non-blocking execution. When you start an asynchronous operation, your program doesn't stop and wait. Instead, it continues running other code while the operation completes in the background. Here's a simple code example showing how future works in Dart. The fetchData function returns a future that will eventually contain a string result, but the program can continue executing other code while waiting for the result. This asynchronous approach is essential for building responsive applications. Whether you're fetching data from a network, reading files, or performing any time-consuming operation, future and stream objects ensure your program remains responsive and efficient. The async and await keywords in Dart provide a powerful way to write asynchronous code that looks and feels like synchronous code, making it much easier to read and understand. Before async and await, working with futures required chaining then methods and handling callbacks, which could become complex and hard to follow. The async keyword transforms a regular function into an asynchronous function. When you mark a function with async, it automatically returns a future, even if you don't explicitly return one. The await keyword pauses the execution of the function until the future completes, but it doesn't block the entire program. Other code can continue running while waiting. Now let's see how async and await transform the complex callback chain into clean, readable code that flows naturally from top to bottom. Notice how each await keyword pauses execution until the future completes, but the code reads sequentially, making it much easier to understand the flow of operations. Let's look at a practical example. Here's a real function that fetches weather data from an API using async and await. To better understand how async and await work, let's examine the execution flow. This flowchart shows the step-by-step process of asynchronous execution. Finally, let's compare synchronous and asynchronous execution patterns. This visualization shows how async operations can overlap and improve performance. The async and await keywords are essential tools for modern Dart programming. They make asynchronous code readable, maintainable, and much easier to debug than traditional callback-based approaches. Dart provides powerful tools for file operations through the Dart.io library. This library gives us everything we need to read, write, and manipulate files in our applications. First, we need to import the Dart.io library. The file class is the main tool we use to represent and interact with files on the system. Creating a file object is straightforward. We simply pass the file path to the file constructor. We can then check if the file exists using the exists method, which returns a future Boolean. Dart provides several methods for reading files. We can read the entire file as a string, read it line by line as a list of strings, or read the raw bytes. All these operations are asynchronous and return futures. Writing to files is equally straightforward. We can write strings, append content to existing files using filemode.append, or write raw bytes. These operations will create the file if it doesn't exist. File operations can fail for various reasons, so proper error handling is essential. Use try-catch blocks to handle common exceptions like file system exception when a file doesn't exist, or path access exception for permission issues. Dart provides both asynchronous and synchronous file operations. Asynchronous methods are recommended because they don't block program execution, leading to better performance and more responsive applications. Synchronous methods should be used sparingly, typically only in command line applications or when you specifically need blocking behavior. Here's a practical example that demonstrates common file operations. This function checks if a file exists, reads its content if it does, or creates a new file with default content if it doesn't. This pattern is very common in real-world applications. File operations in Dart are powerful and flexible. Remember to use the Dart.io library, prefer asynchronous methods for better performance, and always handle potential exceptions. These tools will help you build robust applications that can reliably work with files and data storage. Dart uses a powerful package system to manage shared software, libraries, and tools. Understanding packages and the pubspec.yaml file is essential for building robust Dart applications. Dart packages are reusable code libraries that contain tools, utilities, and functionality you can share across projects. The official repository for Dart packages is pub.dev, where thousands of packages are available. The Pub Package Manager handles downloading, installing, and managing packages. It provides commands like pub get to fetch dependencies, pub add to add new packages, and pub upgrade to update existing ones. The pubspec.yaml file is located in the top directory of your application and serves as the configuration hub. It contains project metadata, dependencies, development dependencies, assets, fonts, and environment constraints. Here's an example pubspec.yaml file. Dependencies are packages your app needs at runtime, like HTTP for network requests. Dev dependencies are tools used during development, like testing frameworks and build tools. Dependencies create complex relationships between files and packages. Each arrow in this graph shows how one file depends on another. The Pub Package Manager handles the entire dependency tree, ensuring all required packages are available and compatible. The package management workflow is straightforward. Edit your pubspec.yaml file, run Dart pub get to fetch dependencies, import packages in your code, and use their functionality. This system provides code reusability, faster development, community support, and automatic version management. The pubspec.yaml file is the heart of every Dart project. It serves as the primary configuration hub, centralizing all the important information your project needs to function properly. Let's examine what a real pubspec.yaml file looks like. This file contains structured information that tells Dart and Flutter everything they need to know about your project. The pubspec.yaml file is organized into several key sections. At the top, we have project metadata that identifies and describes your application. Next comes the environment section, which specifies the Dart and Flutter SDK version constraints. This ensures your project runs with compatible versions. The dependencies section is crucial. It lists all the external packages your project needs to function. These are automatically downloaded when you run pub-get. Development dependencies are packages used only during development, like testing frameworks and code analysis tools. They're not included in the final app. The pubspec.yaml file can also specify assets like fonts and images, making them available throughout your application. This centralizes all resource management. The pubspec.yaml file truly serves as the configuration hub for your Dart project. It centralizes dependencies, metadata, environment constraints, and assets all in one place, making project management simple and organized. Unit testing is a fundamental practice in software development that ensures your code works correctly and maintains quality over time. In Dart, unit testing provides a systematic way to verify that individual components of your application function as expected. But what exactly is a unit in programming? A unit is the smallest testable part of an application. This could be a function that performs a calculation, a method that processes data, or even an entire class that encapsulates specific behavior. Unit testing verifies the functionality of these individual components by running them with specific inputs and checking that they produce the expected outputs. This process helps catch bugs early and ensures that each piece of your code works correctly in isolation. In Dart, the test package provides a standard and powerful way to write unit tests. This package offers a clean syntax for organizing tests, making assertions, and running test suites. It's the foundation for ensuring your Dart applications are reliable and maintainable. Unit testing brings numerous benefits to code quality. It helps detect bugs early in development, provides confidence when making changes, serves as living documentation for your code, and enables safe refactoring. By writing comprehensive unit tests, you create a safety net that ensures your application remains stable and reliable as it grows and evolves. Writing unit tests in Dart follows a systematic approach. First, we need a function to test. Let's create a simple calculator function that we can thoroughly test. Next, we create a test file in the test directory. The naming convention is to add _test.dart to your original file name. In our test file, we import the test package for testing functionality and our calculator file that contains the code we want to test. Now we write our actual unit test using the test function. We create a test instance, call the method we want to test, and use expect to verify the result matches our expected value. Finally, we run our tests using the Flutter test command. This executes all tests in the test directory and shows us the results, including which tests passed or failed. This step-by-step approach ensures your Dart code is thoroughly tested. Remember to follow the arrange act assert pattern, use descriptive test names, and run your tests regularly during development. Now it's time to put all our Dart knowledge into practice by building a real-world application. We're going to create a command line note-taking tool that demonstrates file handling, argument parsing, and professional development practices. A command line tool is a program that runs in the terminal or command prompt. These tools are powerful because they're fast, efficient, and can be easily automated. They're perfect for tasks like note-taking, where you want quick access without opening a full application. Our note-taking tool will have essential features like adding new notes, listing existing ones, searching through content, deleting notes, and saving everything to files. This gives us a practical example of how command line tools work in real applications. We'll use two essential packages for our CLI tool. The args package handles command line argument parsing, managing flags and options while validating user input. The CLI-util package provides logging utilities, progress indicators, and other common helpers that make CLI development easier. Our development process will follow a structured approach. We'll start by setting up the project structure and configuring dependencies, then implement argument parsing and file operations. Finally, we'll add proper error handling and thoroughly test our application to ensure it works reliably. This project brings together everything we've learned about intermediate Dart programming. You'll apply object-oriented principles, master file handling, implement command line parsing, and create robust error handling. Most importantly, you'll have built a real application that you can actually use and be proud of. The Dart command line interface provides powerful tools to streamline your development workflow. These essential commands will help you create, manage, and test your Dart projects efficiently. The Dart create command generates a new Dart project with the proper structure and files. You can specify different project templates using the template option. The Dart run command executes your Dart programs and scripts. It can run files directly or execute scripts defined in your PubSpec file. Here we can see DartPad, an online environment where you can run Dart code directly in your browser. The Dart run command works similarly in your local development environment. The Dart pub get command fetches all dependencies listed in your pubspec.yaml file. This is essential after adding new packages to your project. The Dart pub upgrade command updates your project dependencies to their latest compatible versions, helping keep your project current with security updates and new features. This PowerShell window shows the Dart pub get command in action. Sometimes you might encounter network errors when fetching packages, which is normal and usually resolves with retry. The Dart test command runs all unit tests in your project. It's crucial for ensuring code quality and catching bugs before deployment. Here's a code editor showing test results. The testing panel on the left shows that all 5 tests have passed, demonstrating successful test execution using Dart test. Several other CLI commands are essential for maintaining code quality. Dart format automatically formats your code. Dart analyze checks for potential issues, and Dart compile creates executable files. These CLI tools form the foundation of efficient Dart development. Use Dart Create to start projects, Dart Pub get after adding dependencies, Dart Test regularly during development, and Dart Analyze to catch issues early. Mastering these Dart CLI commands will significantly improve your development productivity and code quality. They provide the essential tools needed for professional Dart development workflows.